Hi, everybody. Uh, my name is Jeyhun, and I'll present our recent work on ad-hoc shared stream processing. I already presented this work at this year's SIGMOD, so for those who watched that video, you will not miss anything. So imagine online gaming scenarios. For example, PUBG is one representative example. In that game, in that scenario, there's an ad stream. Different ads are shown to users, and also there's a purchaser stream. Game players buy different game packs for the during playing the game. And there's a massive amount of streams are generated, which means that there's a high query and data throughput. And also there's the ad hoc stream queries. What are those ad hoc stream queries? For example, at this time, finance team initializes a join query to analyze the users living in Germany and who buy game packs more expensive than 50 euros. And this is a long-running query. And after some time, psychology team initiates query 2, which is again a join query with different selection predicates on each stream. And they want to analyze the behavior of users which have younger than 18 years old. But after some time, they shut down the query because it's morning and all the children go to school, and hopefully they don't play a game in the school. And also there might be pre-scheduled queries. For example, there are specific sessions in each day. In that sessions, users have a specific rules, or they play in specific rooms. And after some time, these sessions are closed. Predefined sessions. What are the problems? The problems with this scenario is that ad hoc query creation and deletion is costly with current stream processing systems, especially when the stream sources have different selection predicates, and especially those selection predicates are UDFs, user-defined functions. And another problems are consistency or performance, among many. We propose AStream, and for that, we have 3 requirements for ad hoc shared stream processing. The first requirement is integration. So whatever we propose as an ad hoc layer should be integrable on top of the existing stream processing engine. So in that manner, we can benefit from built-in features of SPEs, such as fault tolerance, exactly one semantics, or event time stream processing, and etc. The next requirement is consistency. Basically, ad hoc query creation and deletion must be in a consistent manner, and we must ensure the correctness of results and exactly one semantics. And the last requirement is performance. So current streaming systems, the objective is minimize latency and maximize the query throughput, maximize the data throughput. But for ad hoc SPEs, in addition to those requirements, we have to also maximize the query throughput. So this is our system overview. So basically, we have one shared session. This shared session accepts query stop or query create requests from users, and based on that, it generates query change log, the triangles in the figure. And those query change logs go through the whole topology, and which means they go through the shared selection, shared join, or shared aggregation, and finally router instances. And those operators change their computation semantics based on the change log. So basically, instead of creating a separate logical operator instance per query, we have a big shared operator which serves many users. So, data model. Assume we have at time t1, we create query 1 and query 2. So in that time, assume that those are tuples, t1, t2, t4, and t3 and t4. At that time, we append to each tuple an attribute. We call this attribute as query set. And query set is a bitmap. Each bit in this bitmap shows if that tuple belongs to a particular query or not. What belonging means? It means that if this tuple matches the selection predicate of a particular query or not. For example, 1, 0 means this tuple 1 matches the selection predicate of query 1 and does not match the selection predicate of query 2. Okay, then at time 2, imagine that we have query 2 deleted and new query 3 is added. What we can do? Of course, we will have then a bitmap of length 3 to represent all the queries. And of course, the middle one, which represents the query 2, will be 0. But this might lead to very sparse query set with fluctuating query workloads. But what we propose is when some query is deleted, another query is added, we replace the query index of the deleted query. And with change logs, and this change log triangle represents an encoded information, which queries are changed, which queries didn't change. And based on this information, we can ensure correctness of query results. For example, this change log means that query in the position 1 didn't change. Query 1 didn't change. And query in the position 2 changed. Query 2 changed. Means it's deleted or it's updated. Computation model. So all of our operators, which are aggregation and join operators, are windowed operators. And we basically divide those windows into non-overlapping slices. For example, those yellow boxes are windows, and those lines show non-overlapping slices, like these ones. And let's say we want to compute the shared join, and we have to employ incremental computing techniques. How we can join it? At this point of time, query 2 window is finished. So we join slice 2 of A with slice 2 of B, and it's emitted. At this point of time, query 1's window is finished. And we have to join slice 1, 2, 3 of A and B. So basically, because we already joined slices 2, we don't we reuse them. We use this intermediate result to compute the result of joining slices 1, 2, 3, basically to compute the result of query 1. And this continues like that. And afterwards, when this slices are not needed, we just delete them. And what about the joining of these slices? Like how we do join those two slices? So basically, the data structure of slice, we group each tuple, or all the tuples, based on their query set attribute. So basically here, tuple 1 and tuple 2 has the same query set, which means that those tuples belong to query 1 and doesn't belong to query 2. And the same for here. And if we want to join slice 1 and slice 2, before joining all those tuples aggressively, first we want to check that if those tuples, tuple 1 and tuple 2 and tuple 7 and tuple 8, have anything in common in terms of query. Do they share any query? How we can check that? By simply AND product. AND product 1, 0, 1, 0 is 1, 0. It's greater than 1, so they have something in common. So we have to join those two tuples. But what if there's a change log in between? Like there's a change log, which is, let's say, 0, 1. Then, to find the common queries, we AND product also the change log. And in this case, the result is 0, which means that those two slices have nothing in common in terms of query. Those two tuples, the tuples in those slices belong to different query sets. So we can easily eliminate the computation. We can easily avoid the redundant computation by doing this simple AND product. So a little bit of implementation details. We designed our solution as a composable layer over stream processing engines. In this case, we implemented it on top of Flink, but we show in the paper also that it can be also integrated with Apache Spark, Trill, and etc. It's also, we also show in the paper that it's also possible to share aggregation queries. And we have a whole bunch of optimizations like incremental query processing, redundant copy and shuffling elimination, dynamic slice data structure, and we also ensure the correctness of results and exactly one semantics. And also all of our operators are deterministic, which means that in case of a failure, they will produce the same amount, the same results when the data is replayed. So a little bit of experiments. So we run experiments on 4 and 8 node cluster setups. We compare our result with Apache Flink. We have 2 workloads. In the first workload scenario 1, the queries increase up to some point, and they stay stable. And the scenario 2, the query workload, it fluctuates all the time, but the overall query parallelism is less than scenario 1. And this is our benchmark setup. Basically, we have driver generates tuples and queries. And the system under test pulls tuples and queries from the driver and computes. So this figure shows overall data throughput. And this legend, for example, here shows we submit 1 query per second up to 20 query parallelism, 10 query per second up to 60, and 100 query per second up to 1,000 query parallelism. And basically, we can see that AStream has a little bit of overhead with a single query when compared with Flink here. But beginning with the 2 queries, it outperforms the baseline. And another point is that deployment latency for Flink is really high. For example, if we want to submit 1 query per second up to 20 queries, the latency of just query deployment latency will increase for each subsequent query. While in our solution, it will stay in the order of milliseconds. And this is our results for workload scenario 2, in which the queries are fluctuating. And we can see that the overall data throughput is a little bit low than the workload scenario 1, and the reason is that the query parallelism is not that high, and queries are short-lived in this scenario. But event time latency is lower than workload scenario 1. And the reason is that, again, the queries are short-running queries, which means that we have a smaller footprint on the query set and change log. We have smaller change logs. And this leads to better event time latency. And in conclusion, we propose AStream, the first distributed ad hoc stream processing engine. And we show in the paper that state-of-the-art SPEs not only should minimize latency and maximize throughput, but also maximize the query throughput in order to meet ad hoc query environments. Our solution supports majority of stream use cases, including window joins, window aggregations, and combinations of them. And we ensure ease of integration, correctness, consistency, and high performance. Thanks a lot for your listening, and I am open for questions.
Thanks very much. Are there any questions in the audience? Okay. If not, then sorry.
Is the project on GitHub available, or?
It will be on GitHub, but now we are working on the continuation of this project. Once it's done, we will merge both of them and put it on GitHub.
Okay, thanks.
Sure.
Any other question? Okay, so thanks again for the presentation. Thanks everyone for the last few days, and yeah, have a nice evening and rest of your day. Thank you.
Thank you.